Yeah, so hi, yeah, thanks for coming. Today I'm going to be talking a bit about math from the perspective of, visual design, I guess, and how to think about math as another kind of visual element in the different things that you have to do as an academic. Although there's a couple of disclaimers. The main focus, I guess, here is going to be focused on paper writing. So that's probably one of the main ways in which academics have to communicate anyway, but I think a lot of the stuff anyway applies more broadly. A very big disclaimer is that a lot of the stuff here comes from an NLP/applied machine learning perspective. So depending on the field, obviously, things will change. I think NLP is quite interesting because it offers a very big range of expertise in terms of the audience. Like you'll have people that have less exposure to math, but have many other more advanced sort of exposures in other ways. But then you'll have people that are extremely technical and have a very big exposure to math. These things will change a bit. How you want to present the math, what kind of math you want to present. So that's something to keep in mind. But if you're in pure math, probably some of these things will change a bit. And a couple of more things, I guess, is that, I'm going to be assuming LaTeX just because LaTeX is the state of the art as far as I know for writing math. I'm sure that, if you're watching this, you're probably used LaTeX before, but if not, we can put up some notes later. And yes, everything here is opinionated and also situation dependent. So what I'm hoping that you get out of this is just some general ideas of areas in which you could improve or change your process or the process by which you write math and papers. I don't think there's going to be anything here that's completely new to anyone, but hopefully at least formalizing some things is what I'm after. Anyway, so I guess I wanted to start off by talking a bit about how you can think about paper writing as in a sort of different way, as optimization, right? I guess lots of fields like optimization problems. Here we can think of it as well. And the idea is we want to maximize the quality of, we want to convey an idea and we want to maximize the quality by which we convey this idea. So that is, we convey it well. But in general, we're constrained in some way. So this can be either in terms of a hard constraint, NLP, a lot of papers have to be either 4 pages or 8 pages. That's a hard limit that the conference imposes. Or it can be a soft page limit where, in general, if we can express something in 2 pages, then let's not try to write 100 pages on it because people will just get, discouraged from reading it. And it's just, in general, inefficient. So in this sense, we want to, convey an idea well within some sort of budget. And in this sense, you start off with an empty document and what you have is, zero quality because you have not conveyed any ideas from this. But I guess your budget is completely available to you, right? You're not using much space. You could write a paper potentially using only text. Some papers that might be fine, others that might be a bit trickier. And you can think of assigning some score to this, whatever that looks like this text-only paper. And it'll vary depending on the content, and also the quality of the writing. But anyway, you can assign some score to it. And you can fill out the 8 pages with this. That's something you can do. But there are other things apart from text that people use, right? We talked about figures earlier. And figures are nice because, as the saying goes, they're worth 1,000 words. I guess it depends on the figure. But in general, you can take a lot of information and cram it into a very small piece of space. And in that sense, we're kind of optimizing the sort of informational density of our paper. And that's great because we can either keep the quality the same or raise it slightly while using less space. And in turn, potentially this space can be used to convey more information via text or via other media. And we further improve the quality. So it's kind of like, yeah, kind of like an optimization problem. I think that's one way of looking at math, in my opinion, because math is ultimately just one other way of conveying information, like text, like figures, and so on. So when adding math to a paper, ideally we want to think about, okay, can adding this increase the quality of what I'm producing, or at least reduce the net space that we're using while maintaining quality? And I guess, yeah, there's lots of cases in which this is not an option. If you have a particular idea, that idea might only be able to be conveyed via math. But I guess it depends on the field we're in, but it's in machine learning and NLP, my experience as well is that sometimes people try to convey an idea using math where actually it probably doesn't need math to be conveyed. And I guess we'll talk a bit more about it, about that in a bit. But first, maybe if you buy this sort of analogy, then you could talk about the characteristics of different medium. Like text has a particular set of characteristics. Figures have a particular set of characteristics. Math as well has some characteristics. I think the main one is that it's so precise. Precise in the sense that if you try to, there are particular ideas that can only be conveyed succinctly and properly only using math. Like take equations like Andrew was saying before. Like if you want to convey a relationship like y equals mx plus b, doing that with text is very hard. Doing that with a figure, you might be able to get away with that with y equals mx plus b, but if you take a very complicated polynomial, like anything that is like, a couple, more than two inputs probably is going to be hard to plot. And there's even more complicated mathematical ideas that you cannot even visualize. So in that sense, math is able to convey a particular set of ideas very precisely. Now the thing with math is, well, it's extremely technical, and I was struggling to find the right word for this. So I'm not 100% sure if technical is the one that I would want to use, so if you have suggestions, let me know. But I guess the point is that there's a higher barrier to entry with math. Like if you want to convey an idea, if there's an idea you can convey both using text or a figure and math, then generally speaking, unless you know your audience has a very particular background in math, you'll probably be better off conveying this idea via other media, like text or figures. They just feel like slightly more universal in that sense. And obviously academic writing is interesting in that we can often assume a background for the audience. So technical writing might be fine. But again, going back, depending on the field, like fields like machine learning and NLP, there's often a wide range of there's an audience that has a wide-ranging exposure and background in math. So often it's not so easy or so clear what how much math you can assume that the audience is comfortable with. So anyway, there's probably more characteristics, but I think that these are two main ones. And I think that bringing this back to the optimization analogy, I think the way we think about math is that ultimately, because it's precise, we can use math to convey precise information. So depending, if you have a very precise idea you want to convey, again, y equals mx plus b, some complicated polynomial, some sort of relationship about, statistical properties of some model, you can use math to convey that information. But you gotta be careful to try to keep it easy to follow. So I guess there's two questions, and the presentation was kind of broken down into two parts. One is, what do I convey using math? And this is field dependent, this is paper dependent, this is dependent on many things. But there's the what, and then there's the how. So the how focuses on, okay, how can we actually try to make it, or how can we employ techniques or small cues, different things, to try to make it so that, this math is something that is not complicated to the point that you lose your audience, which sucks, right? Because then you want people to read what you write. or else what's the point? But anyway, so starting with the what. I think these things are fairly intuitive, and if you think about the information density idea, like if you have an idea that is quite succinct and can be conveyed with math in a smaller amount of space, then yeah, probably you want to do that. And you don't want to look back. And I stress this because I think that for some fields, like it might be obvious, like why would you even put this? But again, I've definitely seen examples of or had discussions with co-authors being like, oh no, we shouldn't add this as an equation, it will discourage people or something. And I'm like, well, I mean, I think it's more about, if it's an idea that can be conveyed better using math than with text, then we should use math. That is the right way of conveying it. So in that case, I think math is great. But obviously it goes the other way around, right? And I guess, again, it's field dependent, but there are definitely papers where people have like a wall of equations to try to describe an idea that's not, I mean, you probably don't need those equations. Like you can get away with just writing this out. And I think there's something to be said about precision, right? Math is great, again, because of precision. You can convey a very precise idea in a way that you can't do with text or figures often. But sometimes you don't need that level of precision. Sometimes, like if you just want to explain some general way in which you've trained a model. Again, I keep going to machine learning, but I mean, there's examples in other fields, I'm sure. Like maybe if just that general procedure, if you only need to get a high level picture, then why do you need equations explaining very specific details? You could include these, but maybe in an appendix. Maybe this is not really needed in the main body of the paper at that particular point in time. So yeah, so I guess that's kind of like another way of arguing against using math. So anyway, I think that sort of covers the sort of the what, the sort of or the when perhaps of when should we use math, when do we not really need math. Maybe I can stop. I'm going to start talking about the how now, but I guess if anyone has any questions, I'm happy to take questions. If not, I will just keep going. Yeah. Okay. So that's the what, I guess. We've decided that we need to convey something using math. And I've used this to sort of express the sort of technical difficulty of math sometimes. I guess that's how some people react to math sometimes. But I mean, it doesn't have to be that way. It can be nice. It can be great. So how do we actually transform the sort of the panic into just a better experience? And I think, again, going back to the optimization analogy, the way I like to think about this is that when we're writing math, I think this applies to any writing in general, but specifically for math, I think trying to be think about it as proactive / defensive, defensively trying to reduce the cognitive load that you impose on the reader for them to understand whatever idea you're trying to communicate. And I think the emphasis here is on proactively, because when you write something, or at least I feel like when I write something, it's easy for you to think, oh, I mean, this is clear. I mean, clear. This conveys the information I want to get across. But ultimately, the way you read the things you wrote is very different from the way that other people will read those things. And to be able to, putting yourself in other people's shoes, I feel like is where the proactively really comes in. And I'll give some examples of that a bit later. But anyway, for this part, I'm sort of going to break it down into 3 different subsections. First is notation. The second one is how math interplays with text. And the final one is going to be some just general practicalities. I think, again, the disclaimers apply because I feel like if you're here, you'll likely have a lot of exposure to math and you've already done a lot of math writing. So basically with all of these, your mileage may vary. It might depend on the field. But I think that a lot of people, for the following things I'm going to talk about, people naturally will do a lot of these, but I think that, at least I definitely have experiences with co-authors that don't do some of these things, which I feel like are at least worth considering, if, maybe if you don't want to implement them. And I mean, at least being aware of them, I feel like, is at least worth for inspirational purposes, perhaps. But anyway, okay, so starting off with notation. I had some figures earlier on, and they were not really actually quite right, because math is never just that equation environment that you put on LaTeX, like on the left. What you really have is more than that. You often need a couple of sentences beforehand to set things up, or a couple of sentences after to explain exactly what different symbols means. And even then, like, there's just context everywhere. So you sort of need to be aware of that context. And that context is sort of falls under that umbrella of writing math, of writing equations. So a lot of those earlier sentences, they focus on setting up notation for equations so you can actually understand that. Because an equation obviously doesn't mean anything completely outside of this context. But anyway, so these are a couple of things that I'm going to be talking about right now. The slide more as a reference, but in general, some of these are fairly intuitive. And actually, I'm just going to go ahead and just dive straight into the first one, which is when it comes to notation, try to introduce it when you need it and not before. I guess this is something that also varies depending on papers. But I think that this is an interesting idea for people to at least consider when they're writing. I think a lot of papers tend to have a section dedicated to notation, and I think that that's fine in certain settings. However, when somebody's reading paper for the first time, often, you need to keep track of this notation in your head. And if you're writing it, you know what the notation is, so this is not a problem. You've been exposed to it so much, you thought about it. It's like, well, engraved in your head. But if you're a reader, you're going to see a symbol, and if you have to see like a million symbols and sort of commit them to memory, quickly you're going to just start forgetting some. That's kind of, I don't know, if people are familiar with computer systems, like cache, you have a limited cache in some sort of sense. And all these you sort of have a dictionary in your head, which is like a sort of, keys being the symbol and then the values being what it actually means. So anyway, whenever you introduce a new thing, a reader is going to have to commit it to memory. And ideally, you want to try to help the reader remember that. Easy way of doing that is don't introduce something before you need it, right? And I think the actual content here doesn't matter as much. But the point is, this was a paper that I recently wrote. And anyway, we had a lot of trouble with the notation in this paper. And it's not ideal. There's definitely a lot to be improved. But one thing that we remember was trying to figure out when to introduce different things. And here's kind of like a reference sort of resolution chart for basically when is something introduced and when is it used. And I think a lot of mathematical writing ends up being like this. Just naturally people will write in this way. But often, sometimes you let something slip, and is worth making sure, being aware of when things are first introduced and when they're actually used. So in this example, you can see you introduce a symbol V for vocabulary, then the T for text length, and then things get used. And just generally, as you go down, you see that something is introduced to be able to introduce something else. And ultimately, this gets introduced for this. There's something to be said about whether you need to introduce all of this to be able to convey the key ideas. So that's something to be said here. A lot is introduced to be able to explain, to basically just talk about one equation. Obviously, there's more after that rely on the same notation. But yeah. There actually is one counterexample of this idea in here, which is something that we struggled a lot with, which is here right in the middle, we talk about something called a unary conditional. And this is a notation that we introduced here, but we don't actually immediately use it. We use it in the section that comes right behind, after this one, which is not too far. And I remember we struggled with where to introduce that. It just happened to be that there was no ideal place for it, and we kind of the best place ended up being here. But anyway, the point being, introducing notation when it's needed and not beforehand can be a great way of helping a reader understand or keep track of notation and also reduce cognitive load. Also, somebody employing notation as soon as it's used means that the reader it's kind of like using an element from the cache. It kind of sort of like enforces it a bit more, and it means that it doesn't get forgotten. It's like sort of memory, right? If you use things that you've introduced, then people remember them easily, with greater ease. Anyway, so that's one thing. Consistency, this one's fairly obvious, I suppose. But if you're going to go through the steps of actually introducing a bunch of notation, then try to actually use it and try to stay consistent to it, as opposed to introducing more notation that is then inconsistent with what you had before. So in this case, again, from that paper, this is not the best notation. We struggled a lot with this. But the point here is that at least if we introduce this complicated thing with a distribution, with a superscript and a subscript, where the superscript means one specific thing, subscript means something else, and just repeatedly using this notation with small variations sort of, in some sense, justifies the fact that you created it. And also, yeah, it means that you're not all over the place. And in general, you just want to do this, right? You don't want to be changing things around too much. So the third thing is conventions. And I don't know, this one to me, I feel like, again, pretty intuitive, pretty self-explanatory, that I feel like, yeah, people will just generally do this naturally. But I still see like this, I mean, I'm just reviewing a batch of papers and like, sometimes people won't do this. But anyway, the idea is that, like, if your field has any established conventions, I feel like you should try to follow them as much as possible. And I mean, more so than just to like do whatever people have been doing. Like, the point of that is that if people are used to a particular notation, then seeing that notation on its own already primes people to expect a specific kind of thing. Like, people have a set of priors in their field, and you want to leverage those priors. So again, this might not be universal, but for machine learning, at least a lot of NLP papers that I read, they use bolding to denote a vector. So if I just see something bold, I mean, it might not be a vector, but I'm already kind of half expecting this to be a vector. And if it is a vector, then great, awesome, okay, I was right. And it's kind of like, okay, you know, I'm understanding something here. Yeah, and like you have others. I mean, random variables are often capitalized in a lot of texts, and I mean, some of them might be a bit more specific, but like, you know, using Q to allude, like that's often used in like variational inference and stuff. So like if you bring it up, you know, maybe in the back of people's heads, they'll be like, oh, maybe there's something to do with variational inference here, which is a connection that you may or may not want to make. But even if you don't mention it explicitly, it kind of helps prime people for what to expect. I think more importantly than trying to, you know, stick to conventions is not trying to go completely against conventions. And again, like there was a paper that I read recently, and like I was so confused when I read it because they introduced a probability distribution. And this was, again, a machine learning paper. For probability distributions in machine learning papers, like specifically PMFs, like there's basically a couple of symbols that I've seen used. Like the first one is P. Like pretty much every probability distribution I see, people use P to refer to it. Q is also used in some settings. I've seen mu, but this paper had a completely different symbol. I can't remember what it was. It was like maybe chi or something. And I think maybe some fields use that symbol, and it's not so uncommon. But they also called it something different. And when I first read it, it took me like probably like a minute or so. I had to go back and actually make sure. It's like, wait, actually, what is this object? Is this actually a probability distribution, or have they defined it? They also called it something else. Or is this something special? And I mean, at the end, I'm fairly sure it was a probability distribution. But the point is, at least one reader would have benefited from them choosing different notation for that. And I'm willing to bet probably more readers would also benefit from that.
It would be fun to have a paper where we replace all notation with some exotic representations.
That is actually a very good idea. Yeah, we probably should do that. Now, I bet that would be a cool experiment. Like you know, everything is correct. All the notation is strictly correct, mathematically speaking, but it's just exotic. Yeah.
They're like dialects of maths.
Yeah, that would be cool. That would be an interesting study, actually. Yeah. Yeah. But anyway, so conventions. Another one is like avoid abusing notation. Again, like pretty obvious if you stop and think about it. People probably do it implicitly. But I mentioned this here specifically because I think it's tempting sometimes to, it's just maybe it's simpler to, write something that is not strictly correct in an effort to simplify the process of writing. But I had an advisor beforehand that just outright banned abusing notation. And every time you would notice any form of it doesn't matter if people say, no, we'll abuse notation slightly in the next section. It's just outright banned. You can never do that. And the idea is that I think ultimately with notational abuse, you're kind of taking a weird stance in the sense that I think it's fine if somebody is not paying a lot of attention, perhaps, and just skimming, and then it might just make sense as you're skimming. But if somebody is paying a lot of attention to what things mean, and really wants to sort of really deeply understand something, then you might be creating confusion by defining the same symbol to mean different things depending on the context, for example. People have to, basically you transfer the responsibility that you have to write, to convey an idea, to convey a mathematical idea, in some sense to the reader, which now needs to be able to disentangle and tell apart what some object, some symbol means depending on context. So it's something to be careful of, and yeah. I mean, still, sometimes, in that very paper that I'm using as a running example, we ended up abusing our own notation that we defined, mostly because, for space constraints, we could just not be strictly correct, and it would look way too hectic if we were completely, completely proper with our notation. So, yeah, I guess there are situations in which it might be hard not to do it, but in general, it's something to be aware of and try to avoid. Okay, another one is just giving things names. So another experiment might actually be interesting to do this, is take a paper and write it and introduce a bunch of notation, introduce a bunch of symbols to denote different things, but don't actually give them names. Just say, this, we define H to be this, we define S to be this, we define that to be that. And again, in some fields that might be fine, but in fields where, or at least in machine learning, where usually these things mean things that we sort of have a conceptual understanding for, we might define a subset S, we might define a word representation H, which is basically just a vector that represents a word. Being able to say, oh, a word representation H as opposed to, oh, we take H and do this, just helps prime people and remind people of what these symbols mean. In that analogy of, everybody has a mental dictionary as they're reading a paper with a bunch of symbols and what they mean, being able to say and give a short description of a symbol right before you state it, or as the paper goes along, emphasize the description of, or emphasize what a symbol means, just helps people remember things better. I think, this is interesting. Even with things like subsets, right? If you write something I don't know, you're just writing a paper and then you say, okay, we define S 1, 5. I think that was the setting in which we had. Strictly speaking, this is stating that this is a subset because this is a set, therefore this is a subset. But just being able to say, oh, this is a subset S, you already, at this point in time, the reader knows, okay, whatever's coming after this, I know that the type of this object is a subset, and it adjusts that internal world model. I don't know. I feel like that helps. And this connects with something I'm going to bring up later, which is redundancy, which is, basically helping people remember things down the line. So, this will help later on. Anyway, so that's the whole section on notation. There's a couple of things. So, feel free to interrupt and if you have any questions or ideas or anything, really. But the next I want to talk about is just how math interplays with text. And I think the sort of advice / suggestions here become a bit higher level or perhaps more opinionated. But anyway, one thing that a lot of people do, and I think that yeah, if you just look a lot of mathematic texts, you'll see this naturally, and I think people do it naturally. But it's worth remembering is that a lot of authors treat math as is just text. Like linguistically, it's almost like a linguistic object. And what I mean by that is, if you read the sentence, and again, it doesn't matter what the content is, but just think about the sentence structure. Then given a pivot point, this, we define this where, like this is a whole, like the math itself becomes part of the sentence. It becomes another linguistic object. Like, you could probably stop and think about what does this mean linguistically, and people will say, well, a lot of equations, they sort of take the role of noun phrases or nouns. This, I think, can sometimes help with the flow of text. Now, there's some people that don't do it, so I guess your mileage may vary and it's opinionated, but I think that this is something to at least consider doing as a way of making things flow naturally. I think that the way that I've heard to check if whether this is happening or not is that, if you're doing this, then you will feel like you need to punctuate the math, like add a comma after an equation and so on. So that's sort of one way of seeing whether, math is getting treated as text. But this is something, to consider. This is definitely subjective, and I've had people that have told me to, like co-authors that have been like, no, I really don't like this. Please change it back. So, this one, take it with a grain of salt.
Yeah. Curious, in which way you can change it back? Like.
Oh, as in so one way that I've had is instead of actually doing this, I've seen we define colon this and then just state the equation. Like the equation is kind of like just given. It's like think of a figure. I don't like it. But you would never inline a figure. You can never put a figure in the middle of a sentence. I guess with math it'd never be that extreme, I feel, but I think that there's degrees of making it more entangled into text versus less entangled into text.
I think that's pretty interesting because it's an extreme case. It's like, we define equation 3, and then we have literally like equation region and equation captions.
I think that would be.
But people never do that, right? I don't feel like this is very intuitive in terms of like, it's like equations kind of like a separate thing in terms of how they interact with text.
Yeah, I think. Well, you mean a separate thing in terms of like
compared to figures and
yes.
tables, right?
Yeah. I think that the contrast with figures I think is really interesting because figures really I have never seen a figure being inlined in any way, and I don't even know what that could look like. Like people have definitely used like symbols, emojis. You can use that sort of stuff, but a proper figure or a table, it's like you could never do that with a table. But with math, I feel like it can be done, and it feels very natural when you do it. Okay, so I mentioned giving things names. I think this ties on nicely with this idea of redundancy, which is, and also this idea of introducing notation only when you need it. Say that you really have no way of introducing some notation at a particular point in time, but you don't use that notation for a while. Then by giving an object a name, you can, re-emphasize what that object is later on. More generally, just if you haven't used notation in a long time, incorporating some redundancy by reminding people in a way that isn't too sort of out of place what that particular symbol means, I think can be a great way of just, again, helping people keep that dictionary in their heads quite fresh. In general, I feel like, I don't know, when I'm reading a paper, ideally, I don't want to keep going back and forth and being like, oh, I forgot what this symbol was, and then just scrolling back a few pages and then just trying to find it again and then zooming back. Being able to just, give something a name opens the possibility of just repeating that name later. And I feel like that generally helps remind people what that object was. Again, pretty intuitive, but every now and then I think, certain papers that I read could definitely, I think they would benefit from something like this. Actually, Tuesday's lecture with Andrew actually covered most of this, so I'm not going to talk about it a bit too much. But annotations are just such a wonderful way of of conveying information or helping convey information. And I think the nice thing, I think with annotations, it's again the thing about sort of informational density in terms of you're paying a price for writing something on a page, and if you want to convey some information, perhaps you can just convey that information by annotating an equation as opposed to writing text for it or adding a figure or something like that. So again, the actual content here doesn't matter as much as basically this is just saying, okay, we have a model and a model has a bunch of parameters. But being able to just here, we're kind of saying, okay, well, clearly these parameters, or not clearly, but to me it feels clear that these parameters are associated with this Gaussian part of the model, and these parameters associated with the categorical part of the model. Again, with the context, perhaps this would be more obvious, but conveying this in other ways would have taken more space. We could also choose not to convey that information, but then it may not become as obvious where each number comes from. If you want to convey it strictly with math without any annotations, then maybe you would have to define two different equations, one equation for the parameters of the Gaussian, one equation for the parameters of this other part, and then just define the sum. But yeah, in this case, I feel like, this case I think is nice because it really kind of illustrates that sometimes annotations go a long way. And obviously there's millions of examples you can come up with this, and people do it a lot on their papers these days. But yeah, and it's super easy to do with LaTeX if you haven't already. Just use underbrace, like \underbrace, open curly, just put your equation, close the curly, and then you put the text in another curly and well, underscore. Anyway, it's super easy to do. I think, yeah, it's great. Also, color was mentioned by Andrew, typography, different ways of just annotating things to explain, to enhance the math. So beyond just writing the idea down. Well, the one thing that was mentioned with regards to color, which I thought was very interesting, is that color also is something you got to be slightly careful with because it draws a lot of attention. So if you pick up a page and you turn, you turn the page and then you see color, generally your eyes will be drawn to it, and it's just like, again, thinking about that cognitive load is just taking a tiny sliver of cognition, of cognitive power from people's heads and sort of steering it towards a region on the page. This may or may not be what you want to do. And I've personally, I've seen papers that really heavily use color a lot. Depending on how much color is used, I do get the feeling that it can be a bit too much and it can end up being a bit distracting, but it definitely varies. It varies, and it definitely varies on the person. So, but annotations in general, definitely worth looking at. Cool. Okay, so just for the final part, just to finish up some practicalities. Not too much here, and again, some of this is obvious, but this is probably the one that I'm most surprised by, which is that sometimes people don't use macros, at least not as much as I think they should. But macros are amazing, and I think you should. I've very rarely regretted creating a macro for something, but I've definitely regretted not creating macros for something in my paper. And I think the power of macros is that it allows you to very quickly change the way you want to illustrate different things, and specifically symbols that recur a lot, or symbols of a particular type. So things like I mentioned earlier that, at least in a lot of papers that I read, vectors are bolded. That's just the way that people illustrate this. Now, obviously, a paper might have hundreds of instances of vectors. Being able to create a macro that is just a macro that you use for vectors means that if you decide to change your mind, then you can very quickly change the way it's typeset. Whereas if you don't use that, then it'll be way, way harder to do it, to change it. You can kind of like compose these macros by defining, macros for particular vectors, and then those macros for, a very specific vector. Maybe you have a vector h that is special to you. It's the word representation, whatever. Obviously, that macro can reference the vector macro, and so on. So you can compose them, and anyway, it makes it so that at least if your advisor tells you like, oh, please don't use bold for vectors, it becomes something that goes from, an afternoon fixing it to a second fixing it. So yeah. And one thing with macros, and this I haven't seen some people do it. I don't know. Maybe people are aware of this, but this XSpace command in LaTeX comes in a package. Sometimes macros will not, when you introduce these symbols, they won't have a space right after the actual symbol. So if you write something like VH, where this is just a bold, well, actually I'm going to do VV. It's just a bold V in the macro, and then you write like R something. It might omit this space, and then it will write it all together. Now there's a few ways of fixing it, but XSpace, if you just define your VV to have that XSpace at the end, then it will automatically add the space. I don't know. This is something that has been helpful, and I think there's other ways of fixing it by like adding like a brace here. But anyway, that's XSpace is, I don't know, I feel like a lot of times I have an issue and then I'm like, oh, how am I going to solve this? And if it's something to do with spacing, like throwing an XSpace in there fixes it. So I figured it's something worth flagging. Cool, so that's macro. So really genuinely use macro. I don't know, like, please use macros. I think it's, or at least for my co-authors, that's the one message I would love to convey to them sometimes. Is just please use macros. Yeah, so, and the final thing I want to talk about is just proofreading. And I think, general proofreading advice applies to math. But I think math is interesting because proofreading math is harder than proofreading your own text. And certain proofreading techniques for text also don't apply to math. So there are a couple ones that I thought are worth mentioning because I think they're somewhat clever, or, I don't know, have helped me at least in the past. And then, so the first one is that, if something isn't immediately clear to you, then it's probably worth taking a deeper look and seeing what the issue is, or if there's something that, is further polishing as possible. What I mean immediately, at least to me, I mean genuinely immediately. Like you're reading a paper, or at least I'm reading something I wrote, and you're scanning, and you can often go through it somewhat fast, especially if it's I don't know, 2 hours to the deadline. But I don't know, at least for me, my experience, sometimes you'll get stuck on something. And it might be something short. It might be a couple of seconds or something. You just you read something and I don't know why, you didn't quite get it, so you went back. To me, at least, that's signal that there's something off there. And the way I think of it is that if it isn't immediately clear to you, the person that wrote the paper and wrote the equations and knows the notation better than anyone else, then the fact that it took you 2 seconds to figure something out might mean that someone else might take a lot longer. And therefore, it's worth taking a deeper look. So that's a little, I don't know, some rule of thumb that I use to try to figure out what to invest time on. More generally, if you have co-authors, then, I don't know, something to me that took me a while to get, and I don't know, I think that this is a really good proxy. When you're writing a paper and you really want to figure out what to invest time on, I think this is great. But if there's anything that wasn't clear to a co-author, then it definitely won't be clear to other people. Because people, co-authors are in the meetings. You talk to them. They're much more aware of the work than anyone that is just going to sit down and read it. So, in general, if something is not clear to one of them, then that's really, really good signal that you really need to invest more time trying to polish it or improve it. I don't know, at least for me, my experience is that often it's more about trying to get co-authors to be honest with you, or be that sort of that the co-authors don't chalk it up to, oh, I don't know, there's whatever reason I didn't understand this, or actually trying to get people to tell you is a tricky part. But this, I think, is extremely valuable, at least for me, as proven. And then another one, and this one is a bit more practical, but I think it's quite cool. And an advisor, my master's advisor, uses this, and I think it's very interesting. But proofreading your own text is quite hard. or proving your own math is quite hard because you wrote it, so you kind of know what you're expecting, and it means that it's very easy to gloss over very tiny things like indexing errors and sums and so on. So what he did, and he has everyone in his group do, is after you preparing a ready for like a paper for camera ready, or submitting it to archive or whatever, actually going through every equation and recoloring it manually using a macro so that it's like a bright red or something, and then making sure that that macro is removed only if somebody else has also checked that equation and thinks it's correct. In his case, he also has it that's sort of like it's senior authors that have to also make sure the math is correct. But you can also do it with just yourself. But there's two things here. There's one, the act of making sure that somebody else also checks it, which I think is great. And then there's also changing the color as a way of just making it so that your brain is not primed to expect something. I don't know. I feel like if an equation involves many things, again, like you might not carefully check the indexing on a sum, but maybe by changing the color, it just changes it ever so slightly so that you pay more attention to these details. It feels less familiar. Your body, your mind spends more time on it, and maybe you'll catch out a mistake like that. So yeah, I guess that's all really. So just summarizing, I think one interesting idea is, yes, trying to see math as another visual element, and what I mean by that is it's just like a figure or text or a footnote, in that it has a particular set of characteristics in terms of what information it can convey and how it conveys this information. It's well suited for particular settings, like settings where you need to convey very precise ideas, but it also has some limitations, like, well, the barrier of entry to math is usually higher, and people without the background might not be as keen as others when it comes to like engaging with it and really diving into the details and trying to understand what idea is getting conveyed. So you got to find the right place for it. But then you can sort of just imagine the process of paper writing in this sense as an optimization problem where you want to maximize the quality of the idea you're trying to convey while minimizing space usage or being constrained to some amount of space. And then when it comes to ways of trying to make it so that the cognitive load on the reader is eased when it comes to communicating some mathematical idea, then generally be careful with notation. Another thing you can play around with is, to varying degrees, try to treat math or think of math as text. Use macros, and also just a couple of proofreading techniques to help you figure out what to focus on when the deadline crunch is starting and you have little time to fix things. Yeah. But anyway, hopefully this was useful. Yeah.